processes like ozonation. We're not going to get to UV, but also heating and chilling, because this is often overlooked. I'm sure Devin will tell us that it should never be overlooked. But some facilities can get in trouble by not doing the proper heat balances and the like. So Delta Hydronics and Devin were nice enough to participate in this. So Devin will be talking about heating and chilling racks. I went to leave. That's a mistake.
Hey, good afternoon, everybody. Like Brian said, my name is Devin Murray. I work for Delta Hydronics, aquatic heating and chilling. I've honestly only been in the industry about 9 months now. My background is in nuclear submarine design, actually. And while it's a more highly regulated industry, I'm very much beginning to realize the complexity of all the systems is similar, if not greater, in a lot of the gas systems that we're analyzing. So, like Brian said, make sure that all those processes are achieved in the most efficient, optimal way, controlling the water temperature with all the inputs from the ambient environment, as well as the rest of the mechanical systems, is very important to understand and control. All right. To just quickly get started, just got a few major points to touch on. I'm going to do a quick crash course in thermodynamics, both as it applies to a general body of water and also more RAS specific. Running through a quick Delta Hydronics equipment sizing approach. There are different ways to do it. This is our way. We think it's the best, obviously. And then going for just the overall heating and chilling system types. I'm not going to get into too much detail on all the different variations on the equipment, but just give a general overview. And then just touch on a few key topics, like Brian said before, that we often see overlooked or incorrectly done for a various system. So key concepts. First one is very basic. Optimal temperature, going to give you efficient growth and keep everything alive. It's pretty basic. No real rocket science there. The second part, though, when you're considering a new RAS design of anything, your heating and chilling loads, if you are going to have them, it's very energy intensive to heat or chill water. So as part of that, the further upstream in the design process, you can start thinking about heating or chilling. Gives us more options. You can incorporate different kinds of equipment, different kinds of energy saving technology, or basically system concepts, and that's really going to hit your bottom line operational cost at the end. So think about it, as far upstream as possible. And lastly, I have a major misconception I think I want to dispel as well today. System volume is a small part of how we size for heating and chilling loads, but it's not the only thing. Our company, we get a lot of our requests saying that I've got a 10,000 gallon tank. What kind of chiller do I need? And unfortunately, that doesn't really tell us much of all what we need to do to adequately size that for your facility or operation. So things like the environment, the amount of replacement water, insulation, your whole filtration system, all that equipment, that has much more impact on the heating and chilling loads than just the volume of water. So key overall concepts. The more technical part of it, you'll just hear me say, got BTUs, British thermal units, generally what we use to size for heating and chilling loads, 8.33 BTUs to heat 1 gallon of water, 1 degree Fahrenheit. Some conversions to other common power units, the other big one, 12,000 BTUs for 1 refrigerant ton. Typically you see BTUs in heating, refrigerant tons in chilling. And then last, for anybody who didn't have to suffer through thermo, Q is energy flow. So you'll see that quite a bit throughout the presentation. All right. Starting, again, just getting into the environmental loads that we try to understand and analyze for any given system. We've got, a very basic tank there, and any kind of tank or body of water is going to have evaporative, solar loads, radiation, convective, and conduction loads. So to quickly touch on evaporation, this is going to be a major chilling load for any kind of RAS system as well. It's going to be based on your surface area of water, the relative humidity, any differential between your air temperature and your water temperature. So the lower the humidity of your air, the more evaporation you're going to encourage, and the larger the temperature differential between your water temperature and your air temperature, higher or lower, again, encourage more evaporation. When we understand that system, we can find the mass flow rate of your water that evaporates into the air, and based on that and the enthalpy of water at the given temperature, we can determine how much heat is being pulled out into the air. So again, evaporation is always going to be a chilling load. A couple quick things to consider, for a given system, for equal volume, less surface area is going to have less evaporation, less heating you'll have to put into main temperature. So if you can have a taller, less diameter tank, that's going to help your evaporative loads, and conversely, if you have a wider tank, you'll see more evaporation. Again, and then with potential to cover tanks, which I know is very kind of few and far between, but that can also help increase the relative humidity local to that tank, and then that's going to really discourage evaporation there and decrease your chilling loads. On the flip side, the other biggest gain, if you have your facility outdoors, is solar gain. Very simple. There's a lot of publicly available information for the kilowatts per day per meter squared any given point on the Earth receives from the sun. So basically, you have to convert that into a heat load for your given surface area of the RAS tanks. When you're bringing that into sizing, you obviously want to make sure your chiller, your heat load is sized for big summer loads that you might ever potentially see, and then you really don't consider it for heating because you got to be still maintaining heat in the middle of the night in the winter. Very basic overall to consider, not a super difficult analysis either. But the other major consideration here is your equipment. So even if your tank and all the storage is indoors, if you have pumps, sand filters, storage tanks outside, they could be absorbing all sorts of solar radiation as well. And then when those filtration systems kick on, you can be dumping a whole lot of very warm water back into your system. So if you have that kind of setup, or that's something that you have seen, insulating that equipment, covering it with some sort of tarp or awning, to really, obviously help keep it out of the sun. Very simple. Last kind of general topic I'll touch on here, just conductive and convective heat transfer. We'll start with the lesser conductive heat transfer, unless you're sitting on some sort of either geothermal well or extremely frozen ground. Doesn't play into the loading that much. What we see is when a system's starting up initially, you have to basically thermally saturate the ground or the tank if you've got concrete pads. But once that reaches equilibrium, that temperature is hard to move. That's a lot of energy. So we don't lose a lot of heat over time through that mechanism. However, the convective losses from the surface of the water can be substantial as well. For an indoor facility, what you'd want to consider is your level of air replacement, how much airflow is going through the system. So the faster that air is going and the higher the temperature differential is between your water and the air, you can lose a lot of heat or gain a lot of heat into your water through convection. So again, other quick things just to keep in mind as you're sizing a system or considering if you can cover or any way kind of slow down the air local to the tanks, probably not that at all possible, but that could definitely substantially limit your convective transfer, and any kind of insulation you can put at the bottom is just going to create a more thermally isolated system there. So those are the very general, any body of water is going to have these kind of heat transfer mechanisms occurring. When we get into looking at a specific recirculating system, the main ones that we will always ask our customers, what's your exchange rate? How much water you're bringing in? What's the temperature going to be? How stocked is this tank? Is it a brood stock tank? Is it a Barrage tank? Then just general filtration system understanding. What's the pumping horsepower? How many UV filters do you have? What's your sand filter setup? And then just any kind of other miscellaneous equipment that you might be incorporating for your facility.